parametric equations. We have the x that deals with our horizontal distance, the y that deals with our vertical distance, and we're going to relate that to projectile motion. So if we're doing horizontal distance as we move, distance is just rate times time. So if we did our horizontal distance x with respect to time, we're looking at that rate. And when we think about the vectors that we just did we represent rate as a velocity? Yeah. So our rate would be the velocity of x with respect to time.
Just do x.
Now, our vertical movement, our vertical distance, generally when we talk about a vertical distance, we refer to height.
Yes.
And when we're talking about height of a projectile motion, of a projectile in motion, that height depends on some things that affect it on this earth.
Gravity.
We do have gravity. We have the initial velocity of the object.
VO and VM.
And then we have the initial height of the object. Okay, so mathematically we're going to deal with it this way. The effect of gravity on an object is -1/2 g, which is acceleration with respect to gravity. And we're going to look at this. You're going to hate it because we're not in science. We're in math.
I'll hate it.
And math deals with the real world. And in this world, in this country, it does. We measure things in feet.
Oh, no.
I know.
I mean, you measure, man.
I'm sorry,
Okay.
did you mean meters?
So, we could do it in meters. What is the conversion here for meters? 9.8. 9.8.
8-1.
Now, in physics, I have heard today that y'all just use 10.
Yep.
Y'all just use 10.
Yeah, we
I never got to use 10. I'm excited that y'all get to use 10. I had to use 9.8. Alright, so it's -1/2 g t squared plus v naught. What does v naught represent? Initial velocity. That is our initial velocity.
We always do VI.
Okay, y'all use VI? There we go. Now I have all the letters. Okay, and then we actually have to have something to represent the height of the object, and that is our initial height.
We didn't have to memorize it.
Complaining is
Because you're not
really getting on my nerves.
Yeah, I'm just saying.
Okay, so our horizontal component is already represented here. Our vertical component is represented here. So it's -1/2 g, and g depends on the problem you're given. Whether you're going to do it in terms of feet or whether you're going to do it in terms of meters. It really just depends on what you're given. So this is our basic setup for our parametric equations that model projectile motion. So everything's going into this form.
This is all. Can we solve the T?
We're going to use some technology to do that in a second.
A T for technology.
Converted into.
All right. So, what happened this weekend, sports-wise?
Patrick, we won the
The
Masters.
Masters.
Blackhawks
All
lost.
right. The Masters. All right. So here we go. If we have to have a projectile in motion today, I'm going to make it a golf ball. All right. I'm going to set that golf ball on a tee.
Oh, that's
Okay. And this is kind of in some grass.
Nice.
All right. So,
That's actually a really good one.
unfortunately, I'm not good at golf, but for the sake of this problem, we'll pretend some things.
Pretty good.
All right.
I went for the first 5 minutes yesterday.
Oh, then I bet you're amazing.
2 days ago, actually. No.
Okay, so we have our horizontal distance, which this ball is going to travel. Okay.
Mine travels farther.
All right. I'm gonna select a 6-iron.
Nice choice.
All right, thank you.
What's a
And
That's not very far for 6.
hold on, I didn't do this.
It's a putter. It's a
Not
putter.
drawn to scale.
I use the black belt.
All right.
You said it's like
Yeah, I
140.
use
So this is going to be my vector that represents the horizontal distance. I'm using a 6-iron. I'm lofting it slightly. So we got a 32-degree angle here. Okay. So I've got my vector that represents the vertical. So I've got the horizontal, I've got the vertical. Alright? Now, I'm a little frustrated, so I'm going to go out and hit this with an initial velocity of 140 feet per second.
You just did in fourth period and you
Is that good?
Alright?
So
So, now, we're going to create the parametric equations that model this situation. So we have two that we need. We need one that represents our horizontal distance, and we need one that represents our vertical distance. So, when we represent our horizontal distance, okay, so that's this way, right? All right, so how do we go this way? It's with respect to time. And how would I represent this velocity? What would my vector? 140. And that is times cosine of
32.
32.
So the y would be sine.
Okay?
God, where are we going now?
We're combining what we did right before spring break with what we're doing now.
What did we do before? Oh, wait. I thought we did bearing.
Okay.
Oh my gosh, it's just so.
Yeah, it just all came together, didn't it?
No,
Okay.
not that. Like that the vector was just. Okay.
Oh, it was just SOHCAHTOA. Yeah, that happened.
I was so
had some break.
Okay. So let's make sure, let's do a quick check on our units here. This is our velocity, so it's in feet per second. This is time, so it's seconds. Alright, so if I multiply feet per second times seconds, let's do a quick unit check. I'm going to end up with feet, which is my distance. I'm happy. Okay? So I'm happy. That's the right unit. All is well. Alright, so let's go ahead and see if we can represent that vertical. Alright, so we know it's going to be -1/2. We're dealing with feet. So what comes next? 32. Alright, t squared plus, okay, the initial velocity
140
times t. So this is going to be 140, you said it, sine of 32.
Good job,
Now I
Paul.
can do it.
Good job, Paul.
Okay? And then our initial height, careful.
H.
Oh, I didn't tell you.
Watch out with the height.
This t is 3 inches.
Doesn't matter.
What?
Okay? So the initial height of the ball off the ground is 0.25 feet. Correct. Alright, so we could actually take this little part right here and just turn it to -16, right?
That's a really tall
No.
It was high grass.
Some people just tease their balls.
I know, I'm just saying.
Yeah.
Some people,
Yeah.
because they can't. I like to hit mine off lily pads.
Alright, so now what are some questions we could answer? One question we could answer from this problem is how long is the ball in the air? Okay, so the ball is in the air until it hits the ground.
On the other side.
Okay, when I said that in second period, Hunter Chu said, I could see myself writing that as an answer. And I was like, yes, I could see that too. Alright, so it's in the ground in the air until it hits the ground. But what do we know about the height of the ball when it hits the ground?
0.
It is
Oh, I
0.
don't wanna do
It is
that.
0. Okay? So we know that the height off the ground is 0. So we know that 0 would equal -16t squared plus 140 sine of 32t plus 0.25. Okay, so how do we solve this equation? Okay, what do you think?
Where did you get -16 from?
It was the -1/2 times 32. Yeah.
Then you can complete the square.
Okay, that is one way. I would just pull out my calculator and find the zeros. Alright? So, let's do it. You're going to find the zeros
Okay.
on the calc.
Use it for y only.
Alright, now,
Only in the y.
guys, will I stay in parametric form to do this?
Yes.
No.
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 I'm not, because I'm only dealing with,
Two variables.
yeah. Now, so really, t is going to be x, even though we know it's t. But to enter it on the calculator, we're going to have to do negative 16 t squared plus. Let's do it. Everyone, not just me. I'm already good at it.
Oh, you keep going. Okay, I get it.
I couldn't even touch that.
Hold on. I've got to do it so you can see it.
Mine's having a regular error. It says the window is out of range or something.
Zoom 6.
I got
Zoom
Zoom
6.
They're only getting bigger too.
I'm just used to typing it out.
all you do is Zoom 6.
Video games go to everything. And he gets an absurd amount of money.
Alright. There's my graph. Okay? So, hopefully your graph looks like my graph. Which one do we want? Do we want this one over here that's really hard to see?
No.
That's kind of hanging out with the y-axis? Or do you want the second
that
one?
one.
Do you want the second one? Alright, so go find that 0.
What if you?
It's
Right here.
4.5.
we be in degrees, right?
Okay, very good. We should be in degree mode because we typed in 32 degrees. So if our calculator's in degree mode,
Oh my God.
Miss Willoughby, it's just not clear to me, sir, on the exam, are you going to put, like, witness which is degree and radian?
probably not.
Okay, so we'll have to know, so put it to radian. Okay.
Don't do it.
Alright, so second calc, choice 2.
Fred will forget this with me.
Alright.
Nope, I'm gonna go for a name. I slept through class yesterday. It was bad. Like, I'm not even kidding. She was like talking about the inferno.
Alright, so here we go.
It's only in the air for 4 seconds.
I just feel like.
Alright, it is.
Wait, what did I do wrong?
You've never seen me play golf.
Not yet.
It's a very shallow.
Julian,
You've never seen me play golf.
Wait, it's only.
Julian,
I got.
I wouldn't go around saying that.
I wouldn't.
Go on saying what?
Everywhere.
Alright, so here we go.
No, think about it.
Our time, which was our x in this case, is 4.64 seconds. Okay?
That is-
Yes, sir.
Yeah, I didn't get that. I got like
It's like
2.95.
Did
I
you put
typed
it in
it
degree
in.
mode?
Yes, in degree mode.
Okay.
It's not parametric. It's not parametric. It's in regular.
Yeah, okay. The X is right outside of that.
Oh.
Yeah, that's
Oh, it's bad. Yeah, that makes sense.
Okay.
I think I don't recalculate.
Oh, I know why.
Okay. Now, I don't know if you noticed, but during the Masters, they kept hitting the ball into the azaleas. The azaleas were beautiful, but they kept doing that.
I watched a little bit of the.
Sometimes they had to knock it through some trees.
No, my
dad got
hit by one.
So, there's some great shots, but let's turn those into some math now. So, let's say, not that I get to tee up if I knock it into the azaleas. I do not get to tee up. I have to hit it where it lies. But let's say, just for not having to redo the problem, we stick here and there's a tree. I have to clear a tree.
How high is this?
Okay?
What's going on?
Alright?
Well, you cleared it already. We see it.
So,
Put it down.
let's see if I can clear the tree.
So you gotta have it like in your X.
Alright.
Find out the
So, this tree is 50 feet high.
That's not high.
Not bad.
Okay, so you
So
just
that
plug it
means
in
that
to go tree.
I have a little
So you just plug it into the
How
Wi-Fi.
far away is plug in?
Okay? And that is something else we need to
So
know.
you just plug in.
How far away are we from the tree?
6 meters.
Okay? That would be mean.
So you use your little distance finder to bring up our distance.
Okay, so we're finding the distance. What do you think a reasonable distance would be that I can loft it up over a tree?
23.
430 meters.
Yeah,
That would be a wedge if it's 25 feet away. I'd go
Yep.
straight up.
all
All right. All right, let's say it's
90 feet.
90 feet. All
All
right,
That's my
guys.
answer.
90 feet away.
Wow.
Okay.
All
All right, so am I gonna clear? Am I gonna clear?
You said it under.
Just don't believe yourself.
It goes 140 feet a second.
Okay,
No,
so
because that's the minimum.
what do we have to figure out? How long it takes us to get to 90 feet? How would we do that?
What the height is
Plug
it?
it into the X.
We would plug the 90 into the X. So 90 equals 140
Cosine 32.
cosine 32.
Times T.
Which is 4.
This is dead.
But we know what T is already.
Would you divide 90 by the 1?
We know when the ball hits the ground. We know how long before the ball hits the ground.
Oh, so
Now we're doing a different question. We're doing a different question. All right, so here we're trying to figure out if we could loft it over this tree, if the tree is 90 feet away. There's so many different ways we could go with this. It's awesome.
So, do we like
How do you
plug that
solve
in, not plug in
time
for
speed?
Y, and then it will keep?
Okay, so I got a time of 0.75 seconds. Did y'all get that?
How'd you do?
0.758 seconds.
Divide 90 by
You did not get that?
I got it.
When you solve this for T?
Oh, I know what.
Okay, cool. All right, now, how do we find the height?
Go to graph and show the value.
Yeah. Okay, so since we already have it plugged in, I really like your approach. We already have the height equation plugged in. So if we go into second trace, which is calculate, and we calculate a value, and we type in 0.758, what is the height?
47 does not clear.
47 feet. Wrong plug, folks. Chose the wrong plug.
At the top, it's probably like thin enough to where you can.
Yeah, it would go through.
I mean,
All
we can
right,
go back there
that's
in the Z
possible.
dimension and see.
So
if
you
we
have
can
to
put
put
that
that metal on the tree to
to
prevent
So,
left for
You have to make a sheet metal tree. Like
So I'd say chance it.
I might want to change my approach. I might want to change my
Maybe
swing.
to 7.
I might want to change my iron.
You might need to get a 5.
Might change a couple things.
This is
All
how
right.
you go for calculator.
Now, how could we find? Not that we know we can't make it over this tree if it's 90 feet away, unless the branches are really sparse at the top. All right. Now, the next thing we could do.
Probably miss. Just throw it.
Oh, and here with enough force, let's go
I don't
straight
think
to
you
the
could.
Yeah, that's what I was
That's
thinking.
true.
Or you can cut down the tree.
Do y'all want to do well on your next assessment?
No.
Yes.
All right. From my feedback today, I would say no is the correct answer.
Yes!
All right.
That means I'm going to do well in my assessment.
All right. Now, another question I could have asked. This one was if the tree was in the middle.
Okay.
Could we have made it over? Yes. Because the maximum height, which you can find on your calculator by doing a max, is 86. So if the tree was directly in the middle of the path, sure, even if it was 50 feet, like we made the one a moment
You
ago,
still clear.
then we clear it, no problem.
86.248.
But our tree was not in the middle. Our tree was a little closer, so we hit it. All right, now the next question is if the ball is in the air for 4.64 seconds, how far is the ball when it lands from where it was hit?
plug it in.
Plug it in.
Just plug it in.
Plug her in.
So if we plug the 4.64 into the X, we get that it is a distance of 555. That is not far. Because when we play golf, we talk in terms of yards.
And
And this is feet. So even I could do
I
this.
can do that with the
probably
putter.
do that.
Some people probably could do it with a putter.
I was kidding.
This is
I did it at mini golf.
183 yards.
This is over a football
Okay,
field.
I know people drive 300 every time.
All right.
I play mini golf.
Okay. So your approach to word problems involving parametric equations and projectile motion is this. One, you need to write the horizontal and vertical equations, which basically comprise our parametric equation, using those vector components of velocity. Okay? That's what we have to do first. We have to create that horizontal, we have to create the vertical, and when we do that, together they make our parametric. Not peri.
Parametric.
Alright, now, then we're going to solve the equation, the question they asked. And they could ask a lot of different things. I gave you one situation. We looked at it, what, 3 different ways? Okay, so we're going to use our calculators, definitely. We're going to be using the zeros, the max. We also use the value button. These are the things that we will use to solve. Okay? All right. Your homework is the worksheet you're about to receive. It is the problems that are on there.
We saw you for the next 60 seconds, so you don't give up.